Thank you for the invitation. My name is Alice-Agnes, and I present today a collaborative study to observationally constrain multi-scale dynamic rupture modeling of the 2019 Ridgecrest earthquake sequence. I would like, among my co-authors, to specifically highlight Taufik Rahman, PhD student at LMU Munich, is the first author of the study. Earthquake dynamic rupture modeling can bridge scales and disciplines. The illustration here is adapted from the SCAG community dynamic rupture code verification exercise, papers led by Ruth Harris, illustrating the typical input and output of a dynamic rupture simulation. Input can include highly heterogeneous and complex subsurface structure, topography, bathymetry, highlighted here as the geology input, initial fault stresses that can lead to highly heterogeneous shear tractions loading these faults, friction experiments constraining how rocks yield and dynamically weaken during earthquake rupture propagation, combined into a computational model and which is used to solve, typically in the time domain, the elastic wave equation, nonlinear coupled to frictional shear failure across the prescribed fault surfaces. The output we're generating can be compared to observables in terms of seismic, geodetic, tsunami observations, or satellite deformation data, and also in terms of earthquake physics and all dynamic processes that are happening across our dynamically rupturing faults. We're integrating and interpreting a full range of observations and touching upon connections with geology, seismology, geodesy, tectonophysics, numeric computing, data science, mathematics, material science, and many more. During the last decade or so, dynamic rupture modeling has been empowered by supercomputing. This is one example of a petaflop scale simulation revisiting the 1992 Landers earthquake, linking 3D spontaneous dynamic rupture simulations across the segmented strike slip fault system with seismic wave propagation resolved up to 10 Hertz, and including topography, rheology, fault plasticity, and viscoelastic attenuation effects. We and our colleagues in the community show that we can use observation constraints, specifically community models, to understand earthquake rupture dynamics and to study trade-offs and test hypotheses. Data integration can, for example, constrain the initial stress and strength of the fault system and can help us to reproduce slip, moment release, shallow slip deficits, off-fault deformation, waveform characteristics, and peak ground velocities to match, for example, GMPEs, which is here illustrated from these Landers dynamic rupture modeling, or fault zone width can be validated with optical pixel correlation methods. Dynamic rupture modeling of the Ridgecrest sequence uses several ingredients. The first one is a geometrically complex 3D fault network. To this end, we construct a non-vertical quasi-orthogonal cross-cutting 3D fault geometry intersecting with high-resolution topography and embedded in a 3D CVMS subsurface model by integrating geological field mapping of rupture traces, geodetic INSAR data, relocated seismicity, and selected focal mechanisms. Our fault structure includes several fault segments that are the base to model both the M6.4 Seals Valley foreshock and the M7.1 main shock. And these faults are not vertically dipping, but are approaching each other in the undulation with depth. Initial stresses are important in this modeling since both events show high sensitivity, specifically in the vicinity of geometric complexities to the 3D stress state, which is in our case consisting of a background loading plus long and short-term static and dynamic stress transfers. All faults are exposed to a 3D tectonic stress state, which is in our case the SCAG stress community model based on Young and Hauks in 2012. I show here how this 3D SCAG stress community model translates into SH max, the direction of the maximum compressive stress, and the S2 ratio, which balances the two largest components of the stress tensor in the principal coordinate system. All faults participate in the two coupled dynamic rupture models. which also incorporate off-fault plasticity. And the model of the 7.1 main shock will see all of the 6.4 co-seismic dynamic and static stress transfers. The model is also loaded by the pre-Ridgecrest co-seismic and post-seismic Coulomb failure stress changes, DCFS, due to previous major earthquakes occurring in the region in the last 1,400 years. This DCFS yields a positive stress redistribution, additionally loading the source region of the 7.1 event. This is a slice of the DCFS we are accounting for at depth 7 kilometers. And this is how the DCFS is projected onto our fault geometry, shown from two perspectives. Fault strength is here constrained following previous work, specifically illuminating rupture cascading during the complex 2016 Kaikoura, New Zealand earthquake. We are assuming apparently weak faults due to the combined effects of severe velocity weakening friction, elevated fluid pressure, and fault geometry. The fault friction we are applying is a rate and state friction law with rapid velocity weakening, but is statically strong, equivalent to static friction coefficient of 0.6. We are assuming depth dependence to constrain the seismogenic depth based on seismicity inferences, and adapted for creep meter and theodolite measurements along the San Andreas fault. We can constrain fault strength based on only 4 parameters and using few static calculations, so not including any dynamic rupture analysis. These 4 parameters are the initial stress. In our case, this is SH max, and the DCFS, which I explained on the previous slide. We assume an Andersonian stress state, so no plunging of the principal stresses loading this fault system. The stress shape ratio, which we also get from the community stress model. And 2 more parameters, which are the relative fault strength of an optimal oriented fault in this 3D loading, and the fluid pressure. We find through simple static analysis that the relative fault strength, which is balancing the stress drop and the strength drop of the dynamic rupture simulation to follow, should be around 0.8. And that fluid pressure is elevated, but still below hydrostatic, and that it has to be slightly decreased, resulting in a slightly higher stress drop for the 7.1 event compared to the 6.4 event. We're using supercomputing for these simulations, but not a lot of it. Our discretization leads to a computational mesh of 10 million high-order elements that resolve geometrically 200-meter spatial sampling on the fault and of topography, but effectively a higher resolution, so we're using a high-order method. We can resolve up to 2 Hertz the wave field in the fault vicinity and a process zone size of 480 meters. We're including off-fault plasticity, deformation, due to the high stresses during earthquake rupture propagation of the off-fault material, and attenuation. The computational cost for both events is around 10,000 CPU hours. This is our preferred scenario of the rupture dynamics of the 6.4 Seals Valley event. You will see 4 perspectives of the same dynamic rupture scenario in this animation, and observe that we model 2 conjugate faults that rupture simultaneously, while only the southwestern segment breaks the surface. In the slip rate snapshots at 2, 4, and 6 seconds, we illustrate nucleation close to the intersection of fault segment F1 and F2, and a pulse-like propagation across F2, leading to pronounced surface rupture on the conjugate segment. We're comparing our final slip distribution to a kinematic probabilistic source inversion, to back projection, to observational inferred moment rate release, and fault surface offsets. In black is our study here and here, whereas the back projection and the kinematic inversion kinematically agree with our inferences. We also find good agreement in terms of ground deformation compared to inside GPS and also in terms of strong motion data, given that this is a forward modeling approach and not an inversion. Here we're comparing static GPS and surface displacements of our model in orange and dark red to ONAVCO data and Sentinel-1 descending track recordings. Here we're comparing continuous GPS and ground velocity measurements in red of our synthetics and in black of observations, bandpass filtered up to 0.5 Hertz. Interestingly, the 6.4 event causes a small Coulomb stress change at the inferred hypercenter location of the 7.1 event. However, considered part of the main fault are stress shadowed in distinction, which is hindering triggered rupture. As we can see in this little inset at the bottom, which is a time series located at the M7.1 hypercenter, fault strength, which is affected by normal stress changes, and shear stress loading affected by dynamic and static stress interaction are not matched, so there's no instantaneous dynamic triggering. In fact, we find that there's additional loading of around 3 megapascal necessary to nucleate the 7.1 event. This is an animation again from 4 perspectives of the 7.1 Ridgecrest scenario. We will see complex rupture, including reactivation of the conjugate fault segment that already broke during the 6.4 event, and rupture tunneling underneath the geometric complexity to propagate towards the south, where it only manifests a large slip on one of the parallel fault segments. Rupture initiates as a crack-like rupture, but quickly turns due to dynamic weakening into pulse-like rupture, interacting with the conjugate intersection, leading to a tunneling effect underneath this geometric complexity and breaking all the way to the southern part of the fault system. Here again, the slip rate snapshots illustrating rupture complexity. We are comparing against back projection and kinematic source inversion, being overall consistent with the kinematics of our model. We are also seeing in black a nice match with fault surface offsets along the fault F3. Moment rate release, you can recover the 2 peaks and the delay caused by the rupture tunneling, and we have an overall rupture time of around 15 seconds, which is slightly slower than most of observational inferences. And I will comment at the end about the potential effects of very near fault zone velocity structure leading to a locally slower rupture speed that is not considered in that model. We also see good agreement in terms of inside GPS and strong motion data. Again, we have an origin magenta our models compared to observations. We have in red our synthetics for continuous GPS and ground velocity. We can compare off-fault damage in terms of the accumulated plastic strain and the shallow slip deficit, which we model in 3D in these models, to a damage proxy map, and we find a drastic increase of off-fault deformation in geometric complex fault regions, which is additionally enhancing geometric barriers and hindering rupture propagation across these geometric complexities. And it's matching nicely with fault zone width mapping. This is a slide explaining the sensitivity of our model to initial assumptions such as fault geometry and the importance of including DCFS in this modeling. This is the preferred slip distribution of the M6.4 CS Valley event. If we would be modeling the same dynamic rupture scenario without accounting for the long-term DCFS change, we would see that we can nucleate rupture, but it would quickly die out, leading to a very small magnitude event and no surface rupture. If you're assuming a different fault geometry, which is in this case based on non-relocated aftershocks and is much more vertical and simple, you'd see that instead of surface rupture along the conjugate fault, slip would be accumulating along the F1 fault, which is parallel to the main fault. In summary, we've been showing you today combined dynamic rupture scenarios of the 2019 CS Valley and Ridgecrest earthquakes, constrained and validated by observations. we have seen a very high sensitivity of these dynamic rupture models to 3D stress state, specifically in the vicinity of complexities in fault geometry. 2 conjugate faults rupture simultaneously in the M6.4 Sears Valley foreshock, and the M7.1 main shock re-ruptures one of the segments of that already ruptured before of the conjugate fault. The 6.4 induces a considerable Coulomb and dynamic stress change in the M7.1 hypercentral region, however, not enough to trigger rupture across the stress-shadowed main fault. Both scenarios match key observations, including magnitude, directivity, off-fault damage, fault zone width, slip distribution, kinematic inversion, teleseismic waveforms, GPS and inside ground deformation, and back projection. The match with seismic and geodetic data is surprisingly fair, given that this is not an inversion. However, we may be missing important near fault zone properties, specifically to capture the observational inferred relatively slow rupture speed. I'm showing here an adapted model, which includes for low velocity fault zone, consistent, which we are now considering and or exploring to reproduce also the lower rupture speeds. I would also like to highlight an oral presentation by undergraduate student Nico Schliever, who's been analyzing synthetic near-field corner frequencies of these dynamic rupture scenarios, revealing very interesting source, path, and side effects manifesting themselves in elevated near-field corner frequencies, specifically in the vertical components of the wave field. These are 2 snapshots of his work of the 6.4 foreshock and the 7.1 May shock, showing this race of elevated corner frequencies correlating with deflection at strong topography, but also with areas of surface rupture and large fault slip, indicating higher frequency radiation. And with this, I thank you for your attention.